So you will hear a lot in today's talk. And he won a lot of different prizes, like a fellowship in Japan, and also a lot of prizes here in ICE-CSIC. So I hope you enjoy the cosmology today, and let's welcome Emilio.
Okay, yes, this is a privilege of older people that have been to so many places, no? Okay, well, this will be a typical pizza seminar, typical in the sense that no technical details, very relaxed and so. And the main question is, what's in a name? And I will defend that a name is merely a label. I will recall some big names of the origins of modern cosmology, and then I will concentrate on the moment when Fred Hoyle said for the first time, Big Bang. What did he mean? Eventually, the Big Bang was carried out by cosmic inflation. Then I will say that inflation should go under this acronym here. I will give reasons for that. And then, okay, here, I will also explain that for over 50 years, the Big Bang model did not contain any Big Bang. So it was the no Big Bang model for 50 years. Good, Linde and company finally put the Big Bang in it, and then I will end with the different actual meanings of Big Bang. The main meaning today is as a singularity. That was not originally, this came later. Before starting today, this will be a relaxed talk, little technical details, and the contents are highly original. What I'm gonna tell you, you won't find it in any ChatGPT or artificial intelligence. So artificial intelligence knows nothing about that. Nothing about that. I am very proud. This is in this paper in Galaxies of this year, what I'm going to say here. Well, what's in a name? The first to ask this was William Shakespeare in Romeo and Julia. That he said, that which we call a rose by any other name would smell as sweet. So if the rose was called in a different way, it would smell as sweet. So the name doesn't contain the properties of the thing that names. It's just a label. This will be the main point. This will be the main point also for Big Bang. This will be the main point. And then one day I discovered, I myself discovered, I thought that maybe Umberto Eco in Il Nome della Rosa referred to the rose, to Shakespeare rose. And indeed, yeah, Umberto Eco referred to Shakespeare because he continued the thing with names. And the thesis of Umberto Eco is that the names, the meaning of the names evolve with time, evolve. But I was happy to find that, oh, maybe this Il Nome della Rosa is the same rose as Shakespeare. And yes, it is. It is, indeed. So, a name is merely a label. It doesn't change the nature or quality of the thing it represents. Juliet, on the sweet-smelling rose, said that which we call a rose by any other name would smell as sweet. And Umberto Eco revives this paradox. A rose, for Eco, symbol of beauty and love, has vanished. Only its name remains. And the thesis is that names survive. Names survive, but meaning fades. The meaning of the name fades with time, changes, evolves. And this is a central theme in Eco's novel, that the meaning of the name can change with time. there is a conceptual kinship. Shakespeare and Echo explore the tension between words and the realities they name. And this I will apply to the name Big Bang, because it's very, very appropriate, to bring these considerations there. Well, to start with, I already in previous pizza talks, I talked about this Stigler's law of economy, that affirms that no scientific discovery is named after its original discoverer. No scientific discovery. So this is the principle, Of course, as every principle, there are exceptions. So the case where it corresponds, those are just the few exceptions of every rule. Consider as an example, just the Higgs boson that everybody knows. Everybody knows that there were many contributions, and important ones, to the concept of the Higgs, of Higgs. At least those here, Anderson, Brown, Engler, Guralnik, Hagen, Higgs, Kibble, Toft, all of them made important, not just, and not copying one from the other, no, independent, important contributions to this concept that now is called the Higgs, the Higgs. For a time it was called Higgs-Kibble. I remember, because I was there when I was a young, and of course there were some names associated, but then disappeared, and only Higgs remained. Well, because it's simple, to call it Higgs. That's all. But it should be called, in fact, in this way, in this way. And in this case, at least the name that remains has some bearing with it was an important contribution, not the only one. But in many historical cases, name had nothing to do with what it names. The common law is that the term Big Bang began as an insult. And this may be true, but is only an irrelevant aspect of the whole issue. There is much more to this. Well, let's go to what happened actually, and that you can recover word by word. Speaking in the famous BBC third program in 1949, and it should be remarked that at that time, Fred Hoyle was not a professor yet. It was an assistant professor, not a professor. And in this program, only professors were admitted. But as an exception, because he was already a clever guy, he was admitted to speak there. And this is what he said. An announcer read the introduction. In this talk, Fred Hoyle gives his reasons for thinking that matter is being created all the time, so that the universe must have had an infinite past and will have an infinite future. And Hoyle started with these words: I have reached the conclusion that the universe is in a state of continuous creation. In a volume equal to 1 pint milk bottle, about 1 atom is created in 1,000 million years. So even he provided the rate of creation. And why was this? Well, he continued. He considered rival theories. We now come to the question of applying the observational test to earlier theories. These theories were based on the hypothesis that all matter in the universe was created in one Big Bang at a particular time in the remote past. Those were the competing, the other things. On passing, he did insult, in a way, his colleagues, using a climb terminology, all routes taken by other theories attempting to incline peak and in seemingly hopeless physics. To add, the new way I'm going to discuss involves the hypothesis that matter is created continually. This is what he said. Now, let's go to that epoch. What were the two competing models? The two competing models were the stationary model. The stationary model was the model admitted by everybody, at that time, the stationary model, because Einstein and all the genius thought that the universe was stationary. Was stationary. It had no origin, and now, but no, there was Hubble's discovery. Hubble's discovery meant what was admitted about Hubble's discovery is that distant objects were going away quickly, were quickly going away. Hubble's discovery thus didn't mean at that time expansion of the universe. It took a long time to understand Hubble's discovery as an expansion of the universe. Hubble himself never believed, that the universe was expanding. Never. And he had very good reasons not to believe it, because he was a physicist, a real physicist. And with these expanding models that were there, with the Hubble's constant that he had, the universe had only 2,000 million years. And there were rocks in the earth that were older, so there were many reasons. So Hubble has to be taken only at face value. Indeed, and this was admitted by everybody, distant objects go away. So how to maintain stationarity? And everybody then tried to maintain stationarity even with Hubble's discovery. One of them was Einstein himself. And also these other guys. So those were the two competing models. Stationary or an origin by Lemaitre and Gamow. In the case of a stationary, you only need to create some matter to compensate for these galaxies going away, to compensate and keep the density constant. And this is what Hoyle said, and this is his calculation. In order to keep the density constant, he had to create this amount of matter. This was the doing. But he said, in the case that you think that the universe had an origin, as in these cases of Lemaitre and Gamow, if you think that the universe has an origin, then you go back to the Genesis, and then you have to create all the matter in the universe at the beginning, as in the Genesis. In the Genesis, you have to do the job of the Genesis and to create everything instantly at the beginning. This was the argument. That matter could be created out of an expansion of space-time, general relativity. This was clear already from 1934 in Tolman's book, Relativity, Thermodynamics, and Cosmology. You see that an expansion of space allows to create matter energy. The total energy of the universe may be zero, because it may be zero at the beginning. Well, as in inflation, you have inflationary theory, as in inflation. So, but this was already in 1934, the idea, of course, not the inflation theory, but the idea that you could have a universe of zero energy was already there, and also the creation through an expansion. We know that as early as 1931, Einstein had been working on a theory of this type. to maintain, and he attempted to create matter using the cosmological constant. The idea was the same as Hoyle's, to keep the universe stationary despite the recession of galaxies observed by Hubble. Einstein's manuscript was found just about 10 years ago, sleeping peacefully in a drawer. He was unable to find a convincing argument and did never submit this manuscript for publication. But he was working on that. Hoyle had much further with the steady-state theory, with Go and Bondi involving quantum creation operator. Hoyle was fully convinced that the Big Bang he proposed as the only solution to substance Lamarck's model could never have occurred if this was absolutely impossible to create all this matter. It was absolutely impossible. And he made this clear when he uttered for the first time the famous word Big Bang. This is impossible Big Bang. You can find the full text of his talk here. So this can be traced back so exactly word by word what Hoyle said. In short, the issue was clear from the beginning. The concept that is now called inflation. I will elaborate on that. It is now called inflation. The idea, this was the idea. But only very few who were familiar could understand that. Nobody could understand. Everyone else, the vast majority, were left with the false image Hoyle intended to fight. That Lemaitre's outburst of a primordial atom that exploded and throw its contents to the full universe, that has nothing to do with the creation thing. That has nothing to do with the real physical thing. Well, John Griffin, in Hoyle's obituary, Stardust Memories, in June 2005, says that in the popular mind, Fred Hoyle is remembered as the prime mover of the discredited steady-state theory of the universe. Everybody knows that the rival Big Bang theory won the battle of the cosmologists, but few, not even astronomers, appreciate that the mathematical formalism of the now favored version of the Big Bang called inflation is identical to Hoyle's version of the steady-state model. Well, now I will elaborate on this. I will elaborate on this section. That Hoyle defended. Hoyle defended that what he wanted to say when he said Big Bang was inflation. It was inflation. Well, to what extent? To what extent? No, word by word, this is actually not true and needs to be explained. Identical is not appropriate here. Let's compare. In steady-state cosmology, a creation field maintains matter energy density constant with h equal h0, whereas inflation in inflation, the scalar field with potential drives exponential expansion for a very short time. Steady state and inflation formalism are very different at the technical level, although they share the Sitter metric as a formal framework. And what I think is that Griffin probably meant the driving idea behind the two theories is the same, the possibility for matter creation out of space expansion. This is already inherent to Einstein's equations for general relativity. The same as the conversion of matter energy and matter into energy and vice versa is also in his formula for special relativity. So from this formula, you arrive to atomic bombs. But there is a wrong way. There is a wrong way. Here you have only the theoretical possibility. And also in general relativity, there is the theoretical possibility of converting the expansion into matter and energy. Maybe he meant that. And this is clear in the second Friedman equation, you know, because you know in general relativity that we have here that matter goes to whether this is the important difference with respect to Newtonian gravity, you know, that you have here the pressure of space-time, the pressure of the reference system here that goes with R. And if you have you can have some negative pressure here and compensate. You can put here an amount of negative pressure and the same amount of positive. This is a simple view of the thing, but it's the essence. It's the essence that you can compare one into the other as in the other equation. Closer comparison. Steady state creation tensor is an ad hoc modification of Einstein's equation that violates local energy conservation to allow continuous matter creation. The creation tensor there is not derived from an action principle. It explicitly violates usual local conservation law necessary to allow for continuous matter creation. In inflation, particle production occurs through energy transfer from the inflaton during the heating phase, right after inflation ends. So the steady state creation tensor violates conservation's law. Inflation fully respects it. So, of course, it's not the same thing. I remember that I explained about this neighboring obituary, and Starobinsky was sitting and we were here, and this, well, you know, this is exaggerated. This is not true. The idea behind, yeah, and now well, let me first summarize. The steady state theory was a failed attempt to realize the possibility inherent to Einstein. There is a possibility, but this was a failed attempt, as he wanted to construct the atomic bomb, and he failed. You know, he failed. Of course, you can do it, but this was not the way. This was not the way. Trading space expansion for matter energy. In contrast, inflation theories eventually succeed, and in a brilliant manner without breaking any basic physical law on the way. Okay. Now, this for me is very important. Yeah, this thing that I am going to say is very important. This is associated to any scientific discovery, theory, you know, general relativity, let's say. There are different stages in that. First is the eureka moment. Eureka moment. I have written lately several things, contributions to divulgate and in different places about eureka moments. Those are extremely beautiful moments. Einstein had the eureka moment one day. I have told also some time, but again, yeah, he was sitting at his office, and then suddenly, he had the most important thought in his full life. The most important. He thought, if at this very moment I would be falling from the roof of my house, I would be falling from the roof of my house, and I had an object in my hand. In my hand, if I turned my hand, the object would continue by my hand. I am falling, yeah, I am falling from the roof of my house. The object would continue by the hand of my hand. Locally, I have eliminated gravity. Gravity has locally disappeared. Because I am in a moving system, just by moving myself, I make gravity disappears. Here, in this eureka moment, in this thought, here is the whole of general relativity, the whole idea as an idea. So the concept is here. There is no more. Of course, there are additional things, of course, you have to put special relativity principle, the relativity principle, not the laws are the same in all the universe and so on. But here, that you can trade gravity by a movement locally. Of course, this is the first step. Fundamental law, the eureka moment, the thought. But Einstein recognized during his whole life that this was there, all the general relativity was there. Well, in a way, in a way. It took them 10 years at least to formulate the equations. When you have the idea, then you have to put these on paper with equations to write them in mathematical language. Even he couldn't have done this without the help of Riemann. Without Riemann, and those mathematics, just to name this, he couldn't have done this. So this idea, this beautiful idea, would have remained there. It's a whole, but first you have to have the language, the mathematics, and then to be clever enough to translate this idea. But there is nothing else. It's just the translation of this idea, putting this in equations. Formulation, equations. Then there are a bunch of subsequent theories and particular cases appear. Of course, now we know, but this gravity is also, these equations are unique or not. It depends, it depends. If you satisfy the cosmological principle, you can say the equations are unique. Even then, you can work with curvatures or you can work with torsions, of course. Things are much more rich, much more rich. But the main idea, the main principle is the eureka moment is something really, And there are several of these eureka moments. Planck, for instance, had an eureka moment also, Planck, and he said the day he put the age, he said to his son, at the night, he met his son and he said to him, today I did a discovery worth of Newton. So they realize this moment that there is a whole new theory there. And then applications, specific fields, practical uses. Now that I'm getting old, I am abusing this eureka moment, because out of the simple thing, the idea that let's here and let's there. But of course, here there is extraordinary work here, extraordinary work. But even then, the principle, this conversion, in this case, that we need for the creation, for creation of pressure to matter energy is there. So the mathematics, the system, the reference system can convert into matter energy, the gravity. So this is the thing.
Emilio, what is this df equals 0?
This here, Pascual Sancho, is an anecdote. One day, Pedro Pascual came to my office when I was a student, and he told me that he had an important differential equation to solve, and he couldn't solve it. And so he went to Sancho, Juan Bautista Sancho Guimerá, a professor in Barcelona, mathematical professor, that then moved, I am talking when I was a student, he moved to Salamanca, from Barcelona to Salamanca, because Salamanca, Salamanca was the cradle of knowledge in Spain. And he founded an important mathematical department there in Salamanca University. But he was for a while in Barcelona, and Pascual went to Sancho with his differential equation if he could solve it. Yeah, and we went to Sancho and we solved this equation that I have here. And Sancho said, Amigo Pedro, of differential equations, there is only one. Of differential equations, there is only one. BF equals 0. This is at the level of what I am saying here. Of course, in essence, if you go to the very essence things, then of differential equations, there is only one. Df equals 0. And Pedro Pascual came to, he was, you see what this guy had told me. You see, they are useless. They don't do nothing. So the different levels, yeah, of what to, the different levels, of course. Even if you know the theory, if you know the equations, then you have to solve the equations of general relativity. This is extremely difficult, so much work to do. And so it may be, you may think that when I say that everything is there in this thought, that everything, all general relativity is there. Yes, but you have to discard in order to extract everything, of course. Yeah, but it's true. One thing is one thing, and the other is the other. The principle is the essence is one. Yeah, and then it comes. So, yeah. Well, further in my paper, I explained how the de Sitter solution of Einstein's equation is related to Fred Hoyle's original steady-state formulation, how to obtain accelerated expansion. So are simple things, So it's a pedagogical, it's a pedagogical paper. How to reconcile energy conservation with meta creation in an expanding universe, the fact that the universe can have zero total energy, and this credit is done to the pioneers of cosmic inflation. Yeah, this was put there at the instance of the referee that he said. You have to also give credit, to be consistent to all the pioneers of cosmic inflation, starting with Demosthenes Kasanas, and as here I have a specialist in this, that was a student of David Schramm, and in 1980 they published already a paper that it's not forgotten, but Alan Good never made reference to Kasanas. This seems strange, and some people say, I have read this, that maybe Good overheard Kasanas and David Schramm discussing, because they were in the same department, discussing about that, and he could have taken some profit of these discussions, in some way. But what really seems a bit strange is that Good mention Kasanas while others do, it's not everything, but he did the first idea. Then, as Starobinsky developed, what is now maybe one of the preferred ways of inflation, Starobinsky inflation. Katsushito Sato proposed inflation in the universe driven by vacuum energy associated with phase transitions, and Andrei Linde produced the new inflation, resolving the problem, the serious problem that appears in the previous version, the old inflation version of Alan Good. And Andreas Albrecht and Paul Steinkart also developed the new inflation independently from Andrei Linde. And I think those are the names. I think those are the names. And in this respect, I would put here inflation with all these initials. I don't know if you agree. Yeah.
Sure.
There are more important names here.
Probably we can
Yeah.
refresh our memory.
Of course, there are always some countries that maybe do not appear in the, but so all these people should be associated with the development of inflation. Yeah. And so the name here would be that. Yeah. Now, well, I am already just going to finish. Names are just labels. Big Bang was a provisional label for a phenomenon now called inflation. So, of course, I put the differences and so and so, and inflation is a development, is a successful development of this idea of creation out of expansion, out of expansion. So those are labels. For instance, another example is Pythagoras' theorem. It has been discovered now that it was known over 1,000 years before Pythagoras. This was very well known, and there are more and more discoveries because first was only one tablet with some examples, but then they have discovered not just a tablet with some examples, but also even a kind of proof of the theorem. 1,000 years ago, before Pythagoras. But the name remains. Yeah. So Pythagoras' theorem doesn't mean that Pythagoras was the first to discover the theorem. This what should be understood. It's just a label. Yeah, Pythagoras' theorem. Okay, a label. Pythagoras had to do with the theorem, yes, but that does not mean that he was the first discoverer. And concerning the Big Bang, if the original meaning was this inflation, now the most important meaning is the singularity, yeah? Also the model, the Big Bang model, and or even a TV program. So the facts in a sequence. George Gamow, a brilliant and funny scientist, adopted the derogatory expression Big Bang. Yeah, so Hoyle said that these people needed a Big Bang, an impossible Big Bang. And Gamow took the name. I will name our model Big Bang model. Yeah. But really, what Hoyle said is that a Big Bang was lacking in the model, Yeah, so, and it was true. Yeah, so, until 1980 or 81, the Big Bang theory originated in Lemaitre's work did not contain any Big Bang. Good, Linde, and the others inserted the Big Bang in it. Inserted the Big Bang in it, inflation. Yeah? This is the Big Bang demanded by Hoyle. On top of solving the matter creation problem, inflation, the true Big Bang, also solved all other problems of the model. So this was exceptional. And actually, when Good introduced inflation, it was not for creating, it was not for the purpose of matter creation and the quark glue and plasma creation. No. It was in order to solve all these problems. But this Big Bang demanded by Hoyle solve the matter creation problem along with all other problems that the previous Big Bang model or no Big Bang model had. Homogeneity, causality. Well, the name Big Bang remains and is very misleading. Because people do not understand that names are labeled. So Big Bang means nothing. Big Bang means nothing. Means nothing. Yeah. You have to attribute, you have to say what it is. But everybody, when you say Big Bang to somebody, he knows already what this is. Everybody knows. When you say Big Bang, everybody knows what the Big Bang is. And so the name plays against the understanding. It plays against the understanding. And people have said this many, many times. He complains that this is very inappropriate name. It was certainly big, enormous, but for the rest, it's inflation. It's big blow, a big blow. In short, for 50 years, the Big Bang model didn't have a Big Bang, and many problems accumulated. In 1980, the Big Bang was incorporated, solving all issues. The final stage, still pending, will be to definitely prove that the Big Bang did take place. Yeah, still to be proven. It was almost proven some 10 or 12 years ago. It was almost proven, but not quite. Inflation that were already happy that still has to be proven. And of course, there are other possibilities now that have appeared, the pulsating universes, and so I am not mentioning all those other things. Yeah. More appropriate term would be, for me, a big blow that inflates the fabric of space. And nowadays, Big Bang, when you say Big Bang, the first meaning that comes to mind is the Big Bang singularity by default. And with this, I finish. Yeah. Thank you for the.
Any questions? Audience?
Okay, I'm gonna ask a question that probably makes no sense, but so rather than a singularity, is it possible to imagine that at some point space and time decoupled and that this thing didn't happen in a very tiny amount of time, but it's just that they decoupled? It looks like it happened in a very tiny amount of time, extension of space.
Well, I have also devoted some attention to singularity. When a singularity in a theory appears, it means that the theory is not true. You cannot apply the singularity to the region or to the place. The theory you cannot apply to the region or to the place where the singularity appears. So all these singularities of Riemann and Penrose, and of course they are singularities, they are important theorems and so and so. But the region where the singularity applies, general relativity is no more valid there. Is no valid. Is no valid. General relativity is a powerful thing, but if you can like to describe an atom with general relativity, go and describe an atom with general relativity. What happened? And if you are not able to describe an atom, this scale with GR, how can you describe the origin of the universe? You go still lower space. But this is recognized. Yeah. So I have mentioned this also several times, that Hawking himself in his webpage when he was alive, he kept a very beautiful webpage, very beautiful webpage, and he described this, that this means simply that the theory has to be improved. The theory has to be improved. So my idea is that we don't have to attribute much sense to singularities. So you have to work harder there. In a way, the singularity in itself, it means nothing. It means So that this thing that the things become infinite and so on, infinite. There are no infinities in physics. There are no infinities. Yeah. All things have some value. So energy infinite has no sense. No. You know, you can ask for the temperature at different stages of the evolution of the universes, yeah, and that space. What was the temperature there? What was the energy involved there? And so, and you never find any infinite. And when you have a singularity that is so beautiful, singularity, enormous thing, that says that the theory fails there. You have to find a replacement. In the case of general relativity, only working with quantum corrections, because we don't have a theory for quantum gravity, but putting some drops of quantum, some quantum corrections to general relativity, these singularities are removed, or of course, they change. Yeah. Maybe some singularities appear at some other place. You know that it's difficult to solve things easily, but you don't have to attribute much sense to a singularity. You have to resolve it in a way or another, to improving the theory, because the singularities should not appear in a workable theory.
More questions? Any questions online?
There is one.
I caught my attention one for the last slide when you mentioned Good's paper from 1981, where he appeared the Big Bang. And can you show that slide, please? That one. So what you mean exactly there in point number 2? That before this paper, astronomer community did not mention the Big Bang word for the Big Bang theory? I'm just asking this because one of the reasons I'm here today was because when I was a little boy, I watched this TV show from Carl Sagan, Cosmos, that was aired in 1980.
Yes.
And it was already mentioning Big Bang and talking about the Big Bang. So I was just trying to understand the sequence of the historical facts and how this came up. And so that's why I was asking what you mean exactly by that.
Yeah. Well, yeah, it depends on what you mean by this Big Bang. It depends on what you mean by this. I am defending that already the original meaning of Hoyle was already the right one of inflation. It was already this inflation to create. But of course, the Big Bang model, the Big Bang model didn't have this stage of didn't have this. Even then, you can understand the expansion of the universe from when it was small, a kind of bang. But it's not the big, it's already is the navy. Yeah. So in the case of Lemaitre, there was a big bang, there was an explosion of the primordial atom. An explosion of the primordial atom. It was a big bang. But what I defend is going back to the origin of the name, because it was Hoyle who said Big Bang. Hoyle said Big Bang. For the first time, Hoyle said Big Bang. And he was meaning this inflation of space in order to create all the matter of the universe. This is what he was meaning. of course, the same name, Big Bang, can have been used by others, in other contexts. Even when people talk about the Big Bang models, all these Big Bang models, well, they said, well, there was a Big Bang. We had an initial state of very much concentration of matter and so, and then became the universe enlarged and so, but this was not the real Big Bang demanded by Hoyle. Not that it could not have been used, the name. It had been used. It had been used. So I am a bit provocative in that, because the Big Bang model, and I said this should be named the no Big Bang model, the no Big Bang model, because it had no Big Bang. Well, it depends on what you mean by Big Bang. What I mean by Big Bang is the original name by Hoyle. The creation, the genesis, creation of the quark gluon plasma. Sure. Creation of the quark gluon plasma. And then when you have the quark gluon plasma, then you go on. And those models started with the quark gluon plasma, started with these stages. Yeah. If you go to the first 3 minutes in one bar, they start with that. Big Bang is the creation out of an expansion. That's inflation. That's inflation. Inflation. This is what. So Hoyle had the primitive idea of inflation, and he tried to realize it, but he didn't succeed. But of course, you can have seen the name Big Bang used before, of course, not with exactly this meaning of inflation, It was.
And we have last one from online.
I can only see one thing. I think that's much for those. Amazing energy and passion. Let's hope for that. Okay.
Let's thank for today's speakers again. Remember to wait for speaker before you enjoy the quiz stuff. Okay. And see you next time.
Is this picture available for everybody?
Yes, if you're enjoying the talk. You can.
Gracias, Emilio. Gracias, Emilio.